Going to make a quick run now through one of our last topics for the semester, which is momentum. It's kind of a word you probably have heard before, but we're going to talk about it in terms of physics. Basic questions are: what is momentum? How do I calculate momentum? And how does the conservation of momentum apply to collisions? This is a big part of what we'll be doing for this week or so. And some of the vocabulary, again, momentum, elastic and inelastic are kind of a big deal with this. And again, conservation, we've seen this word before, but not with momentum. We've seen it with conservation of energy, conservation of mass, etc. So momentum, we use it a lot in just everyday language. Watching a sporting event, they'll talk about the team having the momentum. Usually that means that things are kind of going their way. And just kind of in an everyday language, it's how hard it is to stop something. So if an object has momentum, then usually it's, the object is moving. If it has more momentum than something that has less, that just kind of means it's going to be harder to stop. Scientifically speaking, what's going to make it harder to stop is when it's moving, is the relationship between mass and velocity. So our science-y official definition here with momentum is mass times velocity. Very easy calculation. We've had some math before that involved mass and velocity. That was kinetic energy. Our last test, we had this with kinetic energy is 1/2 mass times velocity squared. So the math is a little different, but the variables are the same thing. So kinetic energy had mass and velocity. Momentum has mass and velocity. Because there's so many different letters already using M for momentum, we don't use an M for momentum. We use a P, and we see this over here in the formula box. So P equals mv. This is our momentum equals mass times velocity. And so it tends to be shortened, P equals mv. Probably don't need to worry too much about momentum units. There's nothing like a Newton or a joule that we use to combine. We just put the units for mass and velocity together. Mass is kilograms, velocity is meters per second. So if you saw kilogram meters per second, that's a mass and velocity stuck together. That's your momentum. So how do we do basic calculations? Nice and easy. If we got a car that's moving 2,000 kilogram car and it's going 15 meters per second, and we want to calculate its momentum. Hopefully we say, oh, let's go look in the sheet and find the formula for momentum. And it's the first one you come to. Plug in your numbers. M is mass, so we're looking for the kilogram. V is our velocity, so we're looking for meters per second. Plug your numbers in, do the math, get a 3,000, we're done. That's it. So typically very simple, straightforward calculations. And if you're asked to compare the momentums of 2 different things or 3 different things or 4 different things, that's all you would need to do is multiply the mass and velocity of each one of them and look at your answers. Right. Conservation momentum is used when we talk about kind of a before and after. And so momentum is neither gained nor lost unless there's some kind of an outside force interfering with things. Simply put, the momentum before something happens needs to equal the momentum after something happens. And again, this is if there's no outside forces or anything kind of coming in or out of it. If we turn this into some mathematical speak, then P, which stands for momentum, the P before is going to equal the P after. And since P equals mv, we could also say the mass times velocity before is going to equal the mass times velocity after. Again, this is most commonly going to come into play when we talk about 2 objects colliding. If you've in my class and you've done the gizmo, then we've already looked at this with 2 objects colliding and how the mass before and after can change. Well, actually, the masses aren't going to change, but the velocities are going to change. So if we put all of this together, it looks kind of a little bit scary, but M is just standing for masses, V's are just standing for velocities. 1 is standing for the first object and 2 is standing for the second object. So the mass times the velocity of one object and the mass times velocity of the second object, if you add those together and they crash, the resulting velocities and masses, when you multiply things together and do the math, you should get the same outcome. And we'll look at an example of this in a minute. A conservation momentum example where we're not really involving any numbers would be thinking about something like firing a cannon. So the momentum of the cannon and the cannonball before and after it was shot. So again, the law of conservation momentum or conservation momentum says whatever momentum we have before should be the same as we have afterwards. So at the beginning of this, at the beginning of the firing, I'll just kind of go back with this. The cannonball is just sitting inside the cannon. There's no motion. And if there's no motion, velocity is 0. If velocity is 0, then there's not going to be any momentum because the cannon's not moving and the cannonball is not moving. And if you add those together, you're going to get 0. Now, after the cannon shoots, it seems weird that the momentum is going to be still the same, because then the cannon is probably going to move just a little bit, and the cannonball obviously should be flying through the air if everything works correctly. However, because they're going in different directions, their velocity components are going to have opposite signs. One's going to be positive and one's going to be negative. The way that this is drawn, the cannon would go to the left. That would be a negative velocity. The ball would go to the right. That would be a positive velocity. And so after firing, since the velocities are going to go in opposite directions, the momentum of the cannon would end up canceling out the momentum of the cannonball. So think about how this happens, because it's mass times velocity. If you're thinking about the cannon, it has a big mass, but when it shoots, it's going to move very little. And so you're going to have a big number times a small number in one direction. The cannonball does the opposite. It's going to have a small mass, but it's going to have a large velocity, and it's going to be in this direction. So basically, this is going to cancel out that because they're going in opposite directions. So the cannon will have momentum, the cannonball will have momentum, but if you added them together, it's still going to add back up to 0. When we talk about collisions and momentum, there's a few vocabulary terms we need to think about. One is the difference between what kind of a system is it? Is it a closed system or an open system? And a closed system, that's basically saying that there's no way that things can get in or out. There's no energy loss or gain. This usually doesn't exist in real life, because usually when things collide or move, you've got heat being generated. But when we do talk about physics, we often try to talk about an ideal situation. And a closed system would be an ideal situation. Most systems, however, are open. So in an open system, energy can go in, energy can come out. So escape is possible. Think of it as a jar. If you've got a closed jar, things can't go in or out. If you've got an open jar, things can. And then we're also going to talk about what kind of a collision is it? Is it elastic or is it inelastic? If it's an elastic collision, then this is like playing pool or billiards, where one ball hits the other one and the energy from one goes directly into the other one. Now, even on here, it says in an elastic collision, there's no loss of energy due to heat. Again, this is going to be kind of ideal. That probably never happens. And what we're going to see here is that things tend to bounce off of each other. So that's why we use the term elastic. It's kind of like rubber band. Things can stretch, things can bounce. The opposite of this will be an inelastic collision. This is when two things collide. They end up sticking together. There's no bouncing off of it. So there's nothing stretchy. There's nothing bouncy going on. This will be like what you see in a car crash. And the math with this is a little bit different than the math with an elastic collision. Typically in an inelastic collision, we do see very easily the loss of energy due to heat and sound. So if you saw two cars crash, energy would be lost in terms of the crumpling of the car and the heat that was being made. So in an elastic collision, you have a formula on your formula sheet that we can use. This is actually something that we saw back on slide 5. So the idea that the mass times velocity of the two objects added together at the beginning would have to equal the mass times velocity of the two objects at the end. All right, this was also typical if you've done the Airtable gizmo of the calculations and things that we were doing with the gizmo. So again, the masses of those gliders didn't change, but the velocities would change once they hit each other. So what kind of a math problem would this kind of look like? So I'll try to work one out with you real quick. So if we have a 1,000 kilogram car traveling at 20 meters per second, and it hits a 3,000 kilogram truck that's going 10 meters per second in the same direction. If the truck is traveling now after the bump, if it's traveling 15 meters per second forward and it's an elastic collision, how fast would the car also be going? So kind of our steps for this, and again, stop and rewind if you need to go back and catch something, but we're going to start with the formula. We're going to plug in all of our numbers, the mass and velocity of the car, the mass and velocity of the truck. And then again, this is a before and after. So afterwards, the masses don't change. The car is still 1,000 and the truck's still 3,000. We don't know how fast the car is going, but we do know how fast the truck is going. So at this point, it just becomes an algebra problem now that we've got everything plugged in. So we're trying to get V by itself. So we need to combine some things. So 1,000 times 20 is 20,000. 3,000 times 10 is 30,000. And then 3,000 times 15 is 45,000. Again, trying to get V by itself so we can combine some things. So if I combine the 20,000 and 30,000, I get 50,000. I then need to subtract off the 45,000 from both sides. and then divide out the 1,000, and that would tell us that the truck or the car was going 5 meters per second. And that seems kind of reasonable because the car was going 20 and the truck was going 10. The truck is now going faster. And so what we should expect is if one object ends up going faster, the other object should end up going slower in an elastic collision. So that's one of the ways you can kind of double check your work with that. The truck goes faster, so the car ends up needing to go slower, and 5 is less than 20. So that seems like a reasonable answer. All right, finally, when we have an inelastic collision, this is when things stick together, like we have in those car crash. The formula is a little bit different. You'll notice that the first part of the formula is exactly the same as the elastic collision, but because the cars stick together, we don't have two velocities. We have one final velocity. So the end part of the after is a little bit different. We just add the masses together because they do stick, and then we just want to say how fast is it going. So again, the math uses a slightly different formula. However, should be kind of simple. So if we took the same example as we had before, but say that, all right, so now they stick together, how fast would they be going if they stick together? So we're going to use the other formula, which is slightly different at the end. Again, we would plug in everything exactly the same at the beginning. Now we would add our two masses together because the car and the truck are now stuck together to add to one another. And then we just start simplifying again, just like we did before. We do the same thing on the left-hand side. Add these together. So 4,000 V. I need to combine my two terms on the left. And then I need to divide out the 4,000 now on the right through some algebra, and we'd get 12.5 meters per second. Again, does that seem reasonable? Well, one of them's going 20 and one of them's going 10, and so we should expect the answer to be somewhere in the middle of that if they're still going in the same direction. So in summary, momentum is just a measure of mass times velocity, and we can use the principles of momentum to predict and calculate what's going to be the speed of certain objects after collisions, and understand that the momentum is going to stay the same before and after a collision.